Every time you terminate an AI agent session, your entire digital workspace state shatters, scattering hours of progress into nothingness. This occurs because tools like Claude Code and the Gemini CLI operate within a transient context window. They are architecturally incapable of persisting project knowledge once the terminal process ends. For developers, this creates a repetitive tax. You are forced to expend thousands of tokens simply re-explaining your codebase and re-onboarding the agent at the start of every new session. To solve this, claude-mem introduces a biomimetic memory layer. It functions like the human brain, which preserves cognitive efficiency by separating high-level mental indices from the energy-intensive retrieval of specific deep-seated details. By decoupling this memory storage from the active CLI, we transition AI agents from ephemeral scripts into state-aware collaborators that maintain continuity across days or weeks of development. The system's primary objective is to provide autonomous coding agents with infinite project memory without ever saturating their limited context windows. It uses 3 pillars: automated event hooks, hybrid storage, and a tiered MCP interface. This architecture achieves a 10-fold reduction in token consumption. We'll trace a payload through each phase, showing this efficiency is the direct result of this specific pipeline engineering. For memory to be reliable, ingestion must be invisible. It cannot depend on the developer to take notes. It must be driven entirely by the agent's own execution lifecycle. claude-mem captures terminal state by injecting 5 distinct execution hooks directly into the CLI process, as shown in this timeline. First, the SessionStart hook initializes the project environment and establishes the baseline context for the work ahead. The user prompt submit hook then captures your specific developer instructions exactly as they were entered. As the agent executes, the PostToolUse hook extracts the raw logs of the agent's actions and any resulting modifications to the file system. Before this data reaches the database, an internal subagent summarizes the raw hook logs, compressing them into a dense semantic observation. Finally, the stop and session end hooks trigger to finalize the data structure and seal the session payload for storage. These 5 hooks ensure that every relevant I/O event is captured, compressed, and preserved before the terminal window is ever allowed to close. Storing code requires more than just semantic similarity. Standard vector databases often fail here because they struggle to distinguish between exact critical function names or specific variable syntax. This is why the system utilizes a hybrid search backend, splitting the data into 2 parallel storage pipelines. In the semantic pipeline, observations are stored in a Chroma vector database, allowing the agent to find conceptually related ideas through dimensional math. Simultaneously, the same data is indexed in an SQLite FTS5 table, providing the high-precision keyword matching required for exact code strings. When the agent queries its memory, the system synchronizes both databases to return a unified set of relevant observations. This dual-layer approach ensures the agent can navigate abstract narrative concepts without ever losing the ability to locate a specific, literal line of code. The primary bottleneck in most RAG systems is the context dump, where raw search results are fed directly into the agent, consuming thousands of tokens instantly. To prevent this, claude-mem uses a 3-layer progressive disclosure workflow, gated by 4 specific model context protocol tools. In Layer 1, the agent uses the search tool to query the hybrid database. It receives only a compact index of semantic matches and their unique IDs. Because only the index is returned, this initial search costs just 50 to 100 tokens per result. In Layer 2, the agent uses the timeline tool to look at the chronological events immediately preceding or following those IDs to establish causality. Only after the agent has verified relevance does it proceed to Layer 3, calling getObservations to load the full semantic data. This tool is strictly limited to fetching data for specific selected IDs. It never permits a bulk dump of raw text into the context window. This 3-layer funnel mimics biological recall by confirming an association before committing the cognitive resources to reconstruct the full memory, resulting in that 10x reduction in token waste. Routing data to a local worker service decouples memory from the terminal instance. This enables endless mode for infinite sessions without hitting context limits. From capture hooks to hybrid indexing and 3-layer retrieval, everything drives persistent, token-efficient memory. If this architecture overview saved you hours of research, hit subscribe. We review high-utility developer tools every week.